Okay, so we have a test coming up. You guys need to understand things like the limiting reactant, theoretical yield, actual yield, and percent yield. If you get that, it's pretty simple. If you can calculate that, you're getting an A on this test. It's a super simple thing. Limiting reactant. First of all, let's talk about what it is a little bit. It's exactly the way it sounds. It's the reactant that limits the reaction. It's the one that runs out first. So reactant that runs out first. Now, once it runs out, it stops the reaction, which means it's the one that determines how much stuff can be made. It determines how much stuff, or in chemistry we call the stuff product, right? Product can be made. It can be made. That is actually called the theoretical yield, which brings us to the next thing that we need to figure out what that means. So let's shrink this, get it out of the way a little bit. Let's bring the theoretical yield up here. Let's talk about what that is. Right. Now that we've kind of said what limiting reactant does, we kind of can figure out what theoretical yield is. It's the amount of stuff, or the amount of product that can be made. But that's only assuming that everything goes perfectly. That doesn't always happen. So you're probably never going to actually have an experiment where you get your perfect theoretical yield. What you usually get is something called the actual yield, which I wanted to move up here. So actual yield. Actual yield is the amount of stuff that you get. The amount of product that you actually get when physically performing the reaction. So to review, the theoretical yield is the amount that you should get if everything went perfect. The actual yield is what you actually get when you do it. The percent yield is the next thing that we calculate, and that's kind of putting these two things together right here. That gets, get rid of that little thing. We don't need that there. I guess I can't get rid of that little thing. That's nice. Anyway, percent yield is just exactly what it is. The percent that the actual yield is of the theoretical yield. So we take that, and it's equal to, we'll do it over here, the actual yield, the amount you really get, divided by the theoretical yield. And then it's a percent, so we need to multiply it by 100. I like how I used that. That was pretty spiffy. That should be really simple. Hopefully it is. If not, come ask me some questions about it, and we'll figure out what to do about that. Okay, this will work a problem. Something that will probably be on the test. And it's also something that's very closely related to one of the problems you did on the worksheet, number 1, where we took calcium hydroxide and used it to neutralize hydrochloric acid. Let's say we want to figure out if it's enough, if we have enough stuff. So let's say we have a spill of 40.0 grams of hydrochloric acid, and we grab 80.0 grams of calcium hydroxide. So we need to convert it and figure out if that's enough. So let's figure out what the limiting reactant is. So we start out, we know that we have 80 grams of calcium hydroxide. And we want to see if that's enough to neutralize, or how much hydrochloric acid that can neutralize. Well, first we need to change it to moles. So you need to look at the periodic table, and you'll see that 74.0819 grams of calcium hydroxide is in 1 mole of calcium hydroxide. Right? And you just look that up. Add them up. It's very simple. Look up calcium, see how much that mass is, add it to 2 oxygens and 2 hydrogens, and you've got the number. Now, we know, according to up here, that every 1 mole of calcium hydroxide reacts with 2 moles of HCl. So we need to know that each mole of calcium hydroxide reacts with 2 moles of HCl. Now we just plug these into the calculator. We take 80, multiply it by 2. You take 80, multiply it by 2, and then divide it by that 74.0819. And you should get 2.160 moles of hydrochloric acid is how much you should make. I'm sorry, that's how much you could neutralize with 80 grams of calcium hydroxide. But we don't know what if that's good or not, because we have this in grams up here. Right? We have 40 grams. We don't know if 2.16 moles is the same as 40 grams. We have to figure that part out. So we take 2.160 moles of HCl and figure out how much mass that is. So we know from the periodic table that each mole of HCl, remember we want to put the moles, whatever we want to cancel, put them on opposite, either top or bottom. If we want to cancel the moles on top, make sure we put moles on the bottom so we can cancel it. And we know that each mole has a mass of 36.461 grams of HCl. We multiply that out, and that'll tell us that with that 80 grams of calcium hydroxide, we should be able to neutralize 78.76 grams of hydrochloric acid. That makes sense? Hopefully it does. So what does this tell us? Well, this tells us that 80 grams of calcium hydroxide we'll be able to neutralize 2.16 moles of hydrochloric acid, which is the same as 78.76 grams of hydrochloric acid. We only have a spill of 40 grams of hydrochloric acid. So it's more than enough to neutralize it, which means that the actual limiting reactant, is which one? Correct, the HCl is the limiting reactant, because we only have 40 grams of it, and we have enough calcium hydroxide to neutralize almost 80 grams. So we have almost twice as much as we need of calcium hydroxide. Plenty of stuff. Right. But now that's not the only question they're going to ask us. They're going to ask us some other things, and that's what we need to figure out too. So the next part of it, so you can see I shrunk everything, got it out of the way a little bit, so there's room to ask this next question. So how much calcium hydroxide is actually left over? If we started out with 80 grams of it and reacted with the 40 grams of hydrochloric acid, how much is left over? Well, we need to kind of figure out how many moles of hydrochloric acid there were to be dissolved or to be neutralized. So we started out with 40 grams of hydrochloric acid, right? And each mole of hydrochloric acid has a mass of 36.461 grams of HCl. Each mole of calcium hydroxide reacts with 2 moles of HCl, which, where did we get that? We got that from right here, right there. Right? We know that 1 mole of calcium hydroxide reacts with 2 moles of hydrochloric acid. Now, from there, we know from earlier that, oops, didn't want to do that, I want to use the pencil, that each mole of calcium hydroxide has a mass of 74.0819 grams. We got the calculator, and we should figure out that we actually use up 40.64 grams of calcium hydroxide. That's how much is used up. Now that kind of probably got confusing. So what we started out with 40 grams of hydrochloric acid. We used the molar mass to figure out how many moles of hydrochloric acid there were. We used the molar ratio of hydrochloric acid to calcium hydroxide to figure out how many moles of calcium hydroxide would be needed theoretically to get rid of 40 grams of hydrochloric acid. Once we figured that out, then we figured out the actual mass of the calcium hydroxide, which was 40.64 grams. Now, we're not done yet. That's how much is used up. We have 80. So to figure out how much is left over, we take 80.0 grams minus 40.64 grams, right? And you get 39.36 grams of calcium hydroxide is left over. Easy? It shouldn't be too hard. I think that's pretty simple. We'll try another one that actually calculates the theoretical yield and the percent yield in just a second. Okay, for this one we're going to take copper oxide solid plus hydrogen gas, H2 gas, and it's going to make solid copper, pure copper, and water, gas, which is steam. Everybody knows that. We're going to take 19.9 grams of copper oxide and 2.02 grams of hydrogen gas and react them. And we need to figure out what is the limiting reactant, and then if the actual yield is 15 grams, what is the percent yield. So this one is pretty easy. It shouldn't be a problem at all. We're going to do it a little bit different. Last time, remember, we compared the two reactants. This time, since we need to calculate what the theoretical yield is, no matter which one's limiting reactant, we're going to do it a little bit differently and see how much copper each reactant can make given how much is there. So we want to start with the copper oxide. We know we have 19.9 grams of copper oxide. We're going to convert that to moles. Well, you go on the periodic table and you figure that each mole of copper oxide has a mass of 79.545 grams of copper oxide. From there, we want to see how much copper can we make over here from this 19.9 grams. So we look at the equation, and you'll see that 1 mole of copper oxide makes 1 mole of copper, which is kind of cool. That makes it really easy. So it's 1 mole of copper oxide over 1 mole of, oops, got that backwards, copper oxide here. I need to get rid of this oxide, like that, because we want to end up with moles of copper as our answer. And that way, when I cancel, you see, I can cancel moles of copper oxide with moles of copper oxide, and cancel grams of copper oxide with grams of copper oxide, and I'm left with moles of copper, which is what we want. Multiply it out, and you get 0.25 moles of copper. So a quarter of a mole, 0.25 of a mole, can be made from 19.9 grams of copper oxide. You can see that stuff's pretty heavy. It's 79.545 grams. There's only 2 atoms in each one. So that's pretty heavy stuff. So the next one is hydrogen. 2.02 grams of hydrogen gas. Right. Well, we need to figure out how many moles that is. So how many moles of H2 is that? You gotta remember that says H2. That part gets tricky. If you look up hydrogen, you see it's like 1.00794, I think it is, grams per mole. But there's 2 of them, right? So we'll make it nice and easy and a little bit simpler, because if we kind of round in the right spot, we get 2.02 grams of hydrogen gas for every mole. Hopefully you see that this is going to make the math a lot easier. And then again, convert it to copper. We know that each mole of copper is made from 1 mole of hydrogen gas. Multiply it out. This one's lots of canceling. Cancel that with that with, oops, forgot to write the moles down there, didn't I? No, that's right, that's what we want. We don't want to do that one. Darn it. That's okay, you can erase it like this. We want moles of copper, so we don't want to cancel that one. That's silly. But we want to cancel the grams here, and we can actually cancel those numbers. We have the same number divided by itself, or one number divided by itself. The answer is 1. So we should get 1.0 moles of copper is how much 2.02 grams of hydrogen can make. Now, which one makes the least? The limiting reactant is the one that makes the least. Which one runs out first? And the limiting reactant is that one, right? So the copper oxide is the limiting reactant. So limiting reactant equals copper oxide. And that's the answer to A. That seems pretty simple, I think. Hopefully that seems fairly simple to everybody. What I'll do is, let's see if we can shrink that a little bit so that we have some more room, and you guys can still see that. It's just hard to write that small. So the next part, we need to figure out what the percent yield is if we have 15.0 grams of actual yield of copper. Well, we know that the most we can make is 0.25 moles of copper. So if we can make 0.25 moles of copper, we have to figure out how many grams that is. So we need to know that each mole of copper has a mass of 63.546 grams of copper. Not a very good 4, but hopefully you guys can read it. Multiply that out, and we get that that is 15.887 grams of copper. Now, that's about the same as the yield, right? Almost. Percent yield is going to equal actual divided by theoretical, right, times 100, which is 15.0 grams divided by 15.887 grams times 100%, which equals 94.4%. And that is the percent yield. That shouldn't be too hard. Hopefully you guys get it.